As we continue our discussion of Lewis structures, we're going to introduce one more idea to go along with the idea of resonance, and that is the idea of formal charge, which will let us understand, when we're looking at resonance structures, which ones are the most important or the most correct or most useful resonance structures that we can draw for a molecule. So when looking at resonance structures, we looked at a atmospheric molecule, ozone. And for formal charge, we're going to look at another molecule, nitrous oxide, N2O, which is also something that has resonance structures, as we'll see. So let's go ahead and draw the Lewis structure. Again, we're going to go through this step by step, our 5-step process. What's the total number of valence electrons here? Well, we have 5 for each of the nitrogen atoms, plus 6 from the oxygen, so that gives us a total of 16 valence electrons. All right. Now, N2O is written in this order because nitrogen is one of the central atoms. One of the nitrogens is the central atom. And so we will put an N on each side and an O on one side. If it was oxygen first, we would write that as ON2 instead. Okay. Or NON or something like that to make it very clear. Okay. So now let's go through our next steps. We'll add our lone pairs to the outside atoms here, and then we'll count and make sure we have enough electrons. 2, 4, 6, 8, 10, 12, 14, 16. So we've got all of our electrons, but we do not have an octet around all of the atoms in our structure here. So we have octets on the nitrogen on the left and the oxygen on the right, but not on the nitrogen in the middle. Now, there are a few different resonance structures we could draw here. So there's lots of different ways that we could share electrons between these atoms to get an octet around the nitrogen atom. So let's explore a few of these. So one is we could take these electrons from the left side here and put them both into bonds with the other nitrogen atom and end up with a triple bond, nitrogen here with one lone pair over here, and oxygen with a single bond and 3 lone pairs over here. Okay, so that's one possible resonance structure that we could have. We could do the exact same thing from the oxygen's point of view. So we could take these and use those to complete our octet. All right, so that would give us nitrogen with a single bond to nitrogen, the triple bond to oxygen. And this also gives us another resonance structure, so we'll write a resonance arrow here, that also satisfies the octet rule for all of our atoms. And the other option, the other option, is we could take one pair from each side to form a double bond on each side instead of a triple bond. All right, we'll just go like this to give myself space. And so we could have N double bonded to N, double bonded to O with 2 lone pairs on each N. Okay, so all of these are valid resonance structures, but the question is which of these is sort of the most representative or the best of these possible resonance structures. Now, when we were looking at ozone, they were pretty much equivalent, right? All of the atoms were the same. They're all oxygen atoms, so they could sort of be shared equally. And many of the other examples we looked at with resonance structures had this similar sort of characteristic where we were looking at the electrons are being shared between the same kinds of bonds. But now we have a difference here. One side we have a nitrogen atom, one side we have an oxygen atom, and their electronegativities are different. And so we need to think about what would sort of they prefer to have more or less electrons associated with them. And to keep track of this, we use this concept of formal charge. And I will emphasize that this is the formal here is important. This is not an actual charge on the atom in question as we go through this process. So these are not ionic compounds where the electrons have been transferred, but this is instead a way of keeping track of how of the relative, the formal charge on the atoms as opposed to the actual charge. Okay, so how do we calculate formal charge? So first, for each atom, we look at, let me make sure I got the list in the right order here. Okay, so determine the number of valence electrons on that atom. In the neutral atom, or I should say in the free atom. So before it's been bonded. So the same way in the first step of Lewis structures where you're adding up all the valence electrons, that same value. So let's look at, say, we'll start with this nitrogen here. All right, so step 1, nitrogen has 5 valence electrons under normal conditions as a free atom. All right, number 2, we're going to count the number of non-bonding electrons. All right, so these will be our lone pairs in our structure for that atom. So in the example we have here, that is 2 electrons on for this nitrogen atom up here. Okay, let's continue on. Now we're going to be looking at the bonding electrons, and we will count the number of electrons in bonds and divide by 2. Now this step may be a little bit confusing, but essentially what we're saying is the way we calculate formal charges is in a bond, the electrons are shared equally. So as we're sort of counting up the electrons that are on the atom, we sort of divide them up. So I'm sort of trying to depict that here and say each atom gets 1 electron for each bond that they form. And so as we're just in this sort of bookkeeping here, we're just saying, in this example with our triple bond of nitrogen, each nitrogen gets 3 of those electrons, and we don't count them twice. Again, not for counting octets, but just for this idea of formal charge. Okay, so for this, we have 6 electrons in bonds, and we divide by 2, so we get a total of 3 electrons. Right, great. And then we want to, our final step to get the formal charge is add up steps 2 and 3 and subtract it from number 1. So in this example here, we will get 2 and 3 here. Oops. Gotta get my pen again. Add these together, we get 5 electrons, and so our formal charge on this particular nitrogen is 5 electrons minus 5 electrons is equal to 0. So if we're sort of determining this, if we're determining this formal charge for this, we would just not write. So with formal charges, we often write them onto the structures just to keep track. This one would not get a charge put on it. Okay, so that is our formal charge for that nitrogen. Now we can go ahead and do this, repeat this process for all the other ones. We can also represent this whole process here in an equation that might be a little bit quicker and easier to remember, which is that you take the formal charge is equal to the number of valence electrons in the free atom minus the number of non-bonding electrons or lone pair electrons plus the number of bonding electrons divided by 2. So this is just the exact same process we just said, but just written up as an equation instead. All right, so in our first example, we got a formal charge of 0 on the first nitrogen atom. I'm going to pause the video here, stop the video here, just to break it up a little bit, but we're going to come back and calculate the formal charges on all the other atoms and all the resonance structures that we looked at, and talk about what it means and how that is going to affect our understanding of the resonance here.